In part one of this lecture, we introduced the concept of colligative properties and talked about vapor pressure lowering, boiling point elevation, freezing point depression. We spent most of the time talking about the vapor pressure lowering. We also introduced a concept that we said we'd talk about later called ion pairing. In part two, we'll spend more time doing some calculations with freezing point depression and boiling point elevation. We'll talk a lot more about ion pairing in solutions of electrolytes, and we'll end with a couple of example problems. The magnitudes of the boiling point elevation and the freezing point depression of a solution relative to that of the pure solvent are of course directly proportional to the concentration of the solute particles in the solution. We have equations here for both boiling point elevation and freezing point depression. Delta TB in the boiling point elevation equation is by definition a positive quantity because we said the boiling point of the solution should be higher than that of the solvent. Now, common sense would tell us that the freezing point depression, delta T sub F, should be negative. We take care of that by putting a negative sign on the right-hand side of the equation. You'll notice there's a negative sign in this equation and there's not in the boiling point elevation equation. In either equation, the small m is simply the molality of the solution, in units, of course, moles per kilogram. In the boiling point elevation equation, Kb is called the molal boiling point elevation constant. It's in units of degrees C per molal. And in the freezing point depression equation, the constant is called the molal freezing point depression constant, units degrees C per molal. Now both Kb and Kf are different for different solvents and are experimentally determined. And finally, the other variable in both of these equations is I, which is called the Van Hoff factor. And this factor is actually an experimentally determined number for a particular solute-solvent combination at a particular solute concentration. However, if necessary, we can take initial common sense guesses as to what these Van Hoff factors should be for various circumstances. Again, this factor I is actually experimentally determined for particular solute-solvent combinations, but not knowing these numbers, the experimental numbers, we can take guesses. So for example, an initial guess for I would be 1 for a non-electrolyte. That would be a substance that dissolves and does not break up into particles. And for electrolytes, I would be, at least as a first guess, the number of ions produced by each formula unit. So in our previous example of sodium chloride, we would guess I would be 2. The Van Hoff factor should be 2 for sodium chloride because it breaks up into 2 ions, sodium ion and chloride ion. So we are now ready to calculate what we would call the expected boiling and freezing points of our two example solutions, 1 molal glucose and 1 molal sodium chloride. So let's start our determination of the expected boiling and freezing points for our two example solutions by starting out and talking about our 1 molal glucose solution. The boiling point elevation for this solution can be calculated using the equation from the previous slide, and I'm simply going to throw some numbers out here. We'll put a 1 in for the Van Hoff factor. We'll use 0.51 degrees C per molal for the boiling point elevation constant, and the solution concentration, the molality, is 1. If we put these numbers in and cancel out molal units, we get a boiling point elevation of 0.51 degrees C. I can do a similar calculation for the freezing point depression using the equation from the previous slide, a 1 for the Van Hoff factor, 1.86 degrees C per molal for the freezing point depression constant, and of course 1 molal for the concentration, and I get a freezing point depression, calculated one anyway, of minus 1.86 degrees C. So you might wonder where I'm getting these numbers for the Kb and the Kf for water. These are experimentally determined numbers and you need to look them up in a table. A typical table that you might see is shown below here. So in this column we have different solvents, and of course our solvent is water. So if you read over to the right for water, the boiling point elevation constant is 0.51 degrees C per molal. The freezing point depression constant is 1.86 degrees C per molal. That's how I got those numbers. And I guessed that the Van Hoff factor for glucose would be 1 because it's a non-electrolyte molecular substance. So with every glucose that goes into solution, you just get one dissolved glucose. So my guess is that the Van Hoff factor here, which should reflect that, should be just 1. If I wanted to calculate the boiling point of the solution from the boiling point elevation, I could also realize that the boiling point elevation would be the boiling point of the solution minus the boiling point of the pure solvent. And of course, the freezing point depression would be equal to the freezing point of the solution minus the freezing point of the solvent. So the boiling points for the pure solvents you can find in the table below. For water, this is trivial because you already know that the normal boiling point is 100 and the normal freezing point is 0. But if you were using different solvents, which I think we will in one of our example problems, you'd want to look up what these normal boiling points and freezing points are. So if we rearrange this equation and solve for the boiling point of the solution, it would of course be the boiling point elevation added to the boiling point of the pure solvent. And in this case, the whole calculation appears trivial because we know the boiling point of the water is 100, and if it goes up by 0.51, which we calculated here, that means the boiling point of the solution would be 100.5. Similarly, for the freezing point of the solution, we can find that by solving for TF of solution out of this equation. And it's simply going to be the freezing point depression plus the freezing point of the solvent. You say, well, how does that work? Well, remember the freezing point depression we calculated is minus 1.86. The freezing point of the solvent in this case is 0. So naturally, that means the freezing point of the solution would be minus 1.86 degrees C. So what we've calculated here is the expected boiling point and the expected freezing point of a solution that's 1 molal glucose. You might want to note here I'm carrying an extra significant figure right here. Let's do the same or similar calculation for our sodium chloride solution. The boiling point elevation here calculation would look identical to the calculation for glucose with one big difference. I'm going to use a Van Hoff factor of 2 here because I'm trying to remember that sodium chloride breaks up into 2 particles in solution, a sodium ion and a chloride ion. So in both the boiling point elevation calculation and the freezing point depression calculation, I'll use a 2 here. So not surprisingly, our delta TB and delta TF for sodium chloride both end up to be just a factor of 2 different from our result for the glucose. Again, the Kb and Kf values are from our table, and our initial guess at the Van Hoff factor for our electrolyte sodium chloride that breaks up into 2 particles in solution would be 2. If we wanted to then calculate the boiling point of our solution and the freezing point of our solution, we could use these equations and the boiling and freezing points for pure water, which we already know what they are. So solving for the boiling point of the solution, we would get around 101 degrees C. For the freezing point of the solution, around minus 3.72 degrees C, again carrying an extra significant figure here for now. So the sodium chloride solution, which has the same molal concentration as a glucose solution, you can see has a bigger impact on the freezing point and the boiling point. I guess I said that backwards. Boiling point and freezing point. Now in the above calculations, as I said, we made educated guesses for the value of the Van Hoff factor I. We said I would be 1 for glucose and I equals 2 for the sodium chloride solution. Now in reality, the value of I is determined experimentally for a specific concentration of solute by comparing the expected or calculated boiling point elevation and freezing point depression values, which is what we calculated here, the expected ones, with the experimentally observed values. So on the next slide, we will attempt to determine the experimental value of I for both of these solutions. To do this, we're simply going to divide the experimentally measured freezing point depression or boiling point elevation by that calculated, assuming that I equals 1, the theoretical value for a non-electrolyte. That maybe made no sense at all, so let's do the example. We're going to say that our Van Hoff factor will be the measured boiling point elevation divided by the boiling point elevation calculated for a non-electrolyte, and or we could do the other, and that would be calculate I by measuring the freezing point depression and dividing that by the freezing point depression we would calculate for a non-electrolyte. Again, let's do some examples to see if this makes any sense. So for our 1 molal solution of glucose, you can recall that the measured freezing point depression from an earlier slide was minus 1.92 degrees C. Our calculated value that we did just on the slide before this, where we assumed that the Van Hoff factor was exactly equal to 1, was minus 1.86 degrees C. So we can calculate I by taking the measured freezing point and divide by, I should say, the measured freezing point depression divided by the freezing point depression calculated assuming that we have a non-electrolyte, or I equals 1. And it turns out that in this case, the value of I comes out to be very close to 1, which is what we would expect for a non-electrolyte. Again, remember glucose dissolving in water would give 1 particle of dissolved glucose for every formula unit of glucose. So yes, we would expect I to be 1 or very close to 1. Let's do this calculation of I for sodium chloride. Again, notice what we're doing is we're using freezing point data here as an example of calculating I. So if you recall from slide number 2, the actual measured freezing point depression for sodium chloride, a 1 molal solution, was minus 3.43 degrees C. And on the slide before this one, we calculated that for a non-electrolyte, the freezing point depression should only be minus 1.86 degrees C. You might say, now wait a minute, why are you using the results for the glucose calculation from the previous slide for the sodium chloride? Remember, the definition of how to get the Van Hoff factor is you take the experimentally determined freezing point depression and you divide by the freezing point depression you would calculate for a non-electrolyte. So for sodium chloride, I'm going to use the measured freezing point depression on the top, and on the bottom I am again, just like with glucose, going to use the freezing point depression calculated for a non-electrolyte, assuming where we assume I equals 1. So when we do this calculation, we get minus 3.43 degrees C, the experimentally determined number, divided by the expected number for a non-electrolyte, we get 1.84. Now you notice that that's very close to 2. So, however, it is less than what we would expect for sodium chloride. So 1.84 is close to 2, but it is measurably less than what we would expect. So the lower than expected value of I for the Van Hoff factor for sodium chloride can be explained by the effects called ion pairing, where we get some ion pairing of sodium and chloride in solution, and it effectively drops the number of particles that are in solution. I think we can illustrate this with some cartoons. Let's suppose you dissolve 10 sodium chloride formula units in water. If you did that, you would expect to get 20 particles, 10 sodium ions and 10 chloride ions. And this would be the case if there was no ion pairing. And we would say the Van Hoff factor for this situation would be 2. Well, in reality, you don't effectively get 20 total particles. You effectively get about 18 total particles, because what happens is it's possible for sodium and chloride to ion pair in solution. Now they're not pairing up to the extent where they come out as a solid, but they're hanging around each other in close enough proximity because they're attracted to each other that they effectively act as one particle. And so what you've done is some of this ion pairing that occurs is lowered the effective number of particles in solution. And so with some ion pairing now, the Van Hoff factor would be less than 2. Well, what evidence supports this kind of explanation for the Van Hoff factor being less than what you'd expect? Well, the first piece of evidence is that the value of the Van Hoff factor seems to decrease at higher concentrations of ionic solute. So there's more ion pairing under more crowded conditions. So if you increase the concentration of the electrolyte, of the ionic compound, in this case sodium chloride, you'd increase the amount of ion pairing just because sodium ions and chloride ions are in closer proximity, and you find that the value of the Van Hoff factor that you determine experimentally gets smaller and smaller at higher and higher concentrations, meaning there's just more ion pairing in solution. The Van Hoff factor also seems to be lower than you'd expect when the ions have higher charges. So we'll see some data on the next slide, but if these ions here had even higher charges than +1 and -1, there's even more motivation for ions to pair up and lower the number of particles, thus effectively making the Van Hoff factor even lower. Let's look at some experimental data. Here's some experimental data, meaning measured data versus theoretical expected values of the Van Hoff factor I for both molecular, non-electrolyte, and ionic electrolyte solutes at various concentrations. So we see here for sucrose at a 0.1 molal concentration, these would be for water solutions, the expected value is 1, and you see no matter what the concentration, it stays at 1. This is a molecular substance. So this non-electrolyte sucrose, which is very much like glucose, it's just a larger molecule, it's a non-electrolyte, has an expected value of I of 1, and that's really what it is at different concentrations. This is very dilute, this is a little more concentrated. For sodium chloride, which breaks up into sodium ions and chloride ions, you'd expect the value to be 2, but it's less than 2, and it becomes even more less than 2. That's probably not a very good way to say that, as the concentration of the sodium chloride solution gets higher. For potassium sulfate, which breaks up into 3 particles, 2 potassium ions and 1 sulfate, the expected value is 3, and you can see that's not quite reached, and the value of I drops as the concentration of the solution increases. For magnesium sulfate, we'd expect the I value to be 2 because it breaks up into 2 particles, but you can see it's less than 2, in fact much less than 2 at higher concentrations. So here are some things to note about this. Again, sucrose is in the class of molecules called sugars. It's larger than glucose, but it's overall similar composition. It's a non-electrolyte, readily dissolves in water. I equals 1, and it seems to stay that way no matter what the concentration. Now, for each of the ionic compounds, the value of I does decrease with increasing molal concentrations, suggesting excuse me, that ion pairing increases as the concentration increases. On the previous slide, we determined I equals 1.84 for a 1 molal solution of sodium chloride. 1 molal would be over here on the chart. We don't have it. You'd expect it to be smaller than the 0.1 molal solution, and it is. Not by much, but it is. Now here's something interesting. If you compare equivalent concentrations of sodium chloride and magnesium sulfate, so both say 0.1 molal solutions, they both have expected values of I of 2 because they break up into 2 ions. But the value of I for magnesium sulfate is really diminished compared to the value of I for sodium chloride, probably because magnesium sulfate solutions have a lot more ion pairing going on because their ions have higher charges. So they're attracted to each other more forcefully than sodium and chloride ions. So the tendency of these to ion pair is much higher in solution, resulting in much lower values of I at similar concentrations. Now, as promised, let's look at a couple of example questions. The first involves antifreeze. Liquid antifreeze products, one would be the commercial product Prestone, are composed primarily of the water-soluble molecular substance and non-electrolyte ethylene glycol. So here's a Lewis structure of ethylene glycol. I left off the lone pairs on the oxygen. There are other non-trivial components in antifreeze to prevent engine corrosion, etc. You can see from the structure of ethylene glycol why it would be miscible with water, because it's capable of hydrogen bonding through these hydroxyl groups. Now, despite the general term antifreeze, these products are intended to both lower the freezing point and raise the boiling point of the solution circulating through your car's cooling system. An optimum mix of antifreeze and water is typically thought to be 50-50, and in this case, actually what's meant is 50-50 in volume, equal volumes, not equal masses of antifreeze and water. What we want to do here for our question is calculate the anticipated freezing point and boiling points in both degrees C and Fahrenheit for a solution prepared by mixing 50 milliliters of ethylene glycol with 50 milliliters of water. Well, what we're going to do here is use the densities of ethylene glycol in water, which you could look up, to convert their volumes to mass. So if you look up the density of ethylene glycol, it's here at 20 degrees. It's over 1 gram per milliliter. For water, slightly less than 1. So if we calculated the mass of our ethylene glycol to 50 milliliters, we could do that and get 55.68 grams of ethylene glycol. The equivalent calculation for water would give us 49.91 grams of water. Now we'll determine the molality of the ethylene glycol solution after the mixing. So to do that, we need the number of moles of ethylene glycol. So we'll take the mass here and convert it to moles using the molar mass of ethylene glycol, and we get 0.8971 moles of ethylene glycol. And now we'll convert our 49.91 grams of water to kilograms of water, and then calculate the molality of the ethylene glycol solution. So we have 0.891 moles of ethylene glycol divided by 0.04991 kilograms of water. That gives us our definition of molality. So we find out this is an approximately 18 molal solution of ethylene glycol in water. And then we can calculate the freezing point depression and the boiling point elevation for this solution. Now, since ethylene glycol is a non-electrolyte, the Van Hoff factor is 1. So the freezing point depression would be minus 1 times the freezing point depression constant for water times the concentration of the solution gives minus 33.5 degrees C. That's quite a freezing point depression. For boiling point elevation, we get 1 times the boiling point elevation constant times the concentration, and we get a boiling point elevation of 9.2 degrees C. One thing you might ask here, when we talk about a 50-50 solution of ethylene glycol in water, is which is the solvent and which is the solute? What I've assumed here is that our solute is ethylene glycol and the solvent is water. But it might not be a bad idea to ask which one of these is the solvent, because we started with equal volumes of each. Well, the answer here is that water is clearly the solvent. And that's because if you actually calculate how many moles of water you have in this 49.91 grams, it turns out to be 2.770 moles of water. Here's the calculation. Compared to just 0.8971 moles of ethylene glycol. So if you're actually counting molecules, there's at least around 3 times as many molecules of water as ethylene glycol in this solution. So I think it's safe to assume that water is the solvent. Well, moving on here, we want to calculate the freezing point and the boiling points for these solutions. Well, we just calculated the freezing point depression and the boiling point elevation. So this is straightforward here. The freezing point of the solution would be the freezing point depression plus the freezing point of just pure water. And this looks like it's a trivial calculation. The freezing point would be minus 33.5 degrees C. If we did the same calculation for the boiling point of our solution, we'd get 109.2 degrees C. It's 9.2 degrees above the normal boiling point of water. We can convert these to Fahrenheit using a simple conversion, and we get that the freezing point of our antifreeze solution is minus 28.3 degrees Fahrenheit, and the boiling point is 228.6. And as you remember, the normal freezing point of water is 32 degrees Fahrenheit. So we certainly have protected the engine against freeze up. The normal boiling point of water is 220 Fahrenheit. So we've raised the boiling point, and this helps prevent our coolant from boiling. Now both the freezing point depression and the boiling point elevation for the premix commercial product, and this is something I actually pulled out of my garage. I bought premixed Prestone antifreeze. It's 50-50 antifreeze water, and it has some data on it. You'll notice that they claim that the freeze-up protection is good to -34. We calculated -28 Fahrenheit, and that the boil-over protection is up to +265, which is significantly higher than what we calculated of 228. Now, some reasons for this discrepancy, especially between our number for boiling point and the number on the bottle here, might be that there are additional additives just beyond ethylene glycol noted on the label, and it's not just rust inhibitors. You'll notice that it says it also contains not only ethylene glycol but diethylene glycol. And the other reason might be, although this reasoning is a little bit flimsy, but I'm going to present it anyway, despite its very high boiling point, close to 200 degrees C, ethylene glycol at higher temperatures may develop a significant vapor pressure when we reached close to the boiling point of water, and then maybe at these higher temperatures it could no longer be considered a non-volatile solute. Remember, we said that all of our assumptions about vapor pressure lowering and so forth are based on the fact that we're using systems with non-volatile solutes. Now, evidence for this theory would be that there's a larger difference between the calculated boiling point and what's on this bottle than between the calculated freezing point and what's on this bottle. However, if you went a step further and actually looked up published vapor pressure data for ethylene glycol at about 100 degrees C, it indicates that the ethylene glycol would only contribute, this would be the boiling point of water, would only contribute about 16 to 25 torr to the vapor pressure compared to 760 torr for water. So it's difficult to know if that has much of an effect. There'd be an effect, hard to know how much. One thing you want to remember about antifreeze is that ethylene glycol is extremely toxic to pets and humans and has the potential of harming unborn fetuses. So that's why you should never allow spilled antifreeze products containing ethylene glycol to remain on your driveway or garage floor, because your pets seem especially attracted to the taste of ethylene glycol, and that's also probably why there's such highly colored solutions. They're usually bright green or bright yellow, so you can see where they are and clean up the spill immediately. So let's finish this part of the lecture, the last part of this lecture, with one more example, which turns out to be fairly important, and a fairly important example. Let's examine how a freezing point depression measurement can allow us to calculate the molecular weight, or molar mass, of a solute. So here's a situation. A known mass, about 153 milligrams of pure codeine, which is a non-electrolyte, is dissolved in 2 grams of chloroform. So chloroform here is our solvent, not water. It's observed that this solution has a freezing point of -64.7 degrees C, and what we want to do is use this information to calculate the molar mass of codeine. And we'll need to lift some information for pure chloroform off the table that we previously used to get information about water. Well, how do we go about doing this? Well, first of all, we can use the freezing point depression equation to calculate the molality of the solution. Well, how do we go about doing that? Well, here's the hopefully now familiar equation for calculating the freezing point depression. And what we can do here is rearrange this and solve for molality. And you say, well, why do we want to do that? Well, the trivial answer to this is that we have the information we need to calculate M, so why not? Well, what do I mean by that? Well, we have the capability of calculating delta TF from the information given, because remember, the freezing point depression is the freezing point of the solution minus the freezing point of the pure solvent. Well, the problem said that the freezing point of the solution was minus 64.7 degrees C, and the freezing point of the solvent is something we can look up. And what you would do is, when you found the table on a previous slide, you'd find out that the normal freezing point of chloroform is minus 63.5 degrees C. So the actual freezing point depression for this solution is minus 1.2 degrees C. I would be 1 because this is a non-electrolyte, and Kf would be 4.68 degrees C per molal. Again, this would be the freezing point depression constant for chloroform, which you would lift off that table. So we have all the tools here we need to calculate the molality of the solution. So let's do that. When we put in the numbers, we end up with 0.256 molal for the concentration, and it will be helpful for us to remind ourselves that this means 0.256 moles of solute codeine per kilogram of solvent chloroform. Okay, so we have the molality of the solution from the data. We still don't have the molar mass of codeine. Well, we have other information we can tinker with. We can actually use the molality that we calculated here and the mass of the solvent given to determine the number of moles of compound in the pure sample, or in other words, the number of moles of pure codeine in our sample. Well, how do we do that? Well, the number of moles of compound we can find by taking the molality, 0.256 moles per kilogram, and multiplying by the number of kilograms of solvent. And we can get that by just taking 2 grams and converting to kilograms for the mass of chloroform. And if we do that, the kilograms cancel and we're left with 0.000512 moles. That would be moles of codeine. So now we have moles of codeine. What are we going to do with that? Well, remember, there's another piece of information here in the problem, and that is we know the mass of the codeine that we used. So what we're going to do is divide the mass of the compound, and we'll actually use the mass in grams. So we're going to convert 153 milligrams to grams, and we're going to divide that by the number of moles of codeine we said we had, because again, the experimental data led us to know that we had this many moles of codeine. We also know that this many moles of codeine has this mass. And what is molar mass? Molar mass is grams per mole. So what we're going to do is just take the mass of the codeine in grams and divide by the number of moles of codeine that this represents, and we get units of grams per mole, or in this case around 300 grams per mole for the calculated molar mass of codeine. And it turns out that the molecular formula of codeine is C18H21NO3, and the molecular weight, which is simply the weight of all of these atoms combined in atomic mass units, is 299.37, which means that the molar mass is in reality 299.37 grams per mole, which is pretty close to the number we calculated using this freezing point depression data.